Next, myself, Arun Ranjan Naik, HOD Electrical Engineering, Nilachal Polytechnic. Today I am going to explain regarding Kelvin's law. So, Kelvin's law for finding economic size of a conductor, let area of cross section of a conductor is A, annual interest and depreciation on capital cost of the conductor is equal to C1, annual running charges is equal to C2. Now annual interest and depreciation cost is directly proportional to the area of conductor, that is C1 is equal to K1 into A, and annual running charges are inversely proportional to the area of conductor, C2 is equal to K2 by A, where K1 and K2 are constants. Now total annual cost C is equal to C1 plus C2, that implies C is equal to K1 into A plus K2 by A. For C to be minimum, differentiation of C with respect to A must be 0. That is dC by dA, derivative of C with respect to A, dC by dA is equal to 0. Therefore, we can write dC by dA is equal to d by dA of K1A plus K2 by A is equal to 0. That implies K1 is equal to K2 by A2, K2 by A square is equal to 0. That implies K1 is equal to K2 by A square, K1 into A is equal to K2 by A, that implies C1 is equal to C2. So the Kelvin's law states that most economical size of a conductor is that for which annual interest and depreciation on the capital cost of the conductor is equal to the annual cost of energy loss. From the above derivation, the economical cross-section area of a conductor can be calculated as A is equal to square root of K2 by K1. Graphical illustration of Kelvin's law. This is the curve drawn between conductor area A with respect to annual cost C. This is the annual cost, total annual cost line. This is the annual cost of the conductor cost C1, annual energy loss C2. This is Y and this is X. As the annual cost of conductor is directly proportional to size of the conductor, it is shown by the straight line C1 in the figure. Annual cost of energy loss is shown by the curve C2. The total annual cost curve is obtained by adding the curve C1 and C2. The lowermost point on total annual cost curve gives the most economical size of the conductor, which corresponds to the intersection point of curve C1 and C2. So here the most economical area of cross section of the conductor is represented by OX, and corresponding minimum cost is represented by XY. Limitation of Kelvin's law. Although Kelvin's law holds good theoretically, there is often considerable difficulties while applying in the practice. The limitation of this law are: it is quite difficult to estimate the energy loss in the line without actual load curves, which are not available at the time of estimations. Interest and depreciation on the capital cost cannot be determined accurately. The conductor size determined using the law may not always be practicable one, because it may not have sufficient mechanical strength. This law does not take into account several factors like safe current, carrying capacity, corona loss, etc. The economical size of the conductor may cause the voltage drop beyond the acceptable limit. Next, modified Kelvin's law. The actual Kelvin's law does not count the cost of supporting structure, erections, insulators, etc. It only accounts for the capital cost of conductor and corresponding interest and depreciation. Also, the underground cable, the cost of insulation and laying is not considered in the actual Kelvin's law. To account for these costs and to get practically fair results, the initial investment needs to be divided into two parts. First, on one part which is independent of conductor size. Second, other part which is directly proportional to the conductor size. For an overhead line, the insulator cost is almost constant, and the cost of supporting structure and the erection is partially constant and partly proportional to the conductor size. So according to the modified Kelvin's law, the annual charge on capital outlay is given as C1 is equal to K0 plus K1A, where K0 is on another constant. The differentiation of total cost C with respect to area of conductor A comes to be same as derived above under the headings Kelvin's law. The modified statements of Kelvin's law suggest that the most economical conductor size is that for which the annual cost of energy loss is equal to the annual interest and depreciation for that part of capital cost, which is proportional to the conductor size. This is annual cost line, this is conductor area, this is C total cost. C is equal to K plus K1A plus K2 by A. This one is the fixed cost line, C1 is equal to K plus K1A. This is another line P2, C2 is equal to K2 by A. Corona effect in power systems. The electric power transmission practically deals in the bulk transfer of electrical energy from generating stations situated mainly kilometers away from the main consumption center or cities. For this reason, the long distance transmission cables are of almost necessary for effective power transfer, which is evident result in huge loss across the system. Minimizing those has been a major challenge of power engineers of late, and to do that one should have a clear understanding of the type and nature of losses. One of them being the corona effect in power system, which has a predominant role in reducing the efficiency of ESV, extra high voltage lines, which we are going to concentrate on this article. What is corona effect in power system and why it is occurs? For corona effect to occur effectively, two factors here are the prime importance as mentioned below. First one is alternating electrical potential difference must be supplied across the line. Second, the spacing of the conductors must be large enough compared to the line diameter. So the transmission lines having how the corona will be produces here. When an alternating current is made to flow across two conductors of transmission line whose spacing is large compared to their diameters, then air surrounding the conductors is subjected to dielectric stress. As the low values of supply and voltage, nothing really occurs as the stress is too less to ionize the air outside. But when the potential difference is made to increase beyond some threshold value of around 30 kilovolt, known as the critical disruptive voltage, then field strength increases and then the air surrounding it experience stress high enough to dissociate into ions, making the atmosphere conducting. This results in electric discharge around the conductor due to the flow of these ions, giving rise to faint luminescent glow, along with the hissing sound accompanied by the liberation of the ozone, which is readily identified due to its characteristic odor. This phenomena of electrical discharge occurring in the transmission line for high values of voltage is known as corona effect in the power system. If the voltage across the line is still increased, the glow becomes more and more intense along with hissing noise, inducing very high power loss into the system, which must be account for. Next factor affecting corona effect in the power systems. As mentioned earlier, the line voltage of the conductor is the main determining factor of the corona in transmission line. At low values of voltage, the stress on the air is too less to dissociate them, and hence no electrical discharge occurs. Since with increasing voltage, corona effect in a transmission line occurs due to the ionization of atmospheric air surrounding the cables. It is mainly affected by the conditions of the cable as well as physical state of the atmosphere. Let us look into this criterion now with greater detail. Next, atmospheric condition for corona in transmission lines. It has been physically proven that the voltage gradient for dielectric breakdowns of air is directly proportional to the density of the air. Hence, in a stormy day, due to continuous air flow, the number of ions present in surrounding the conductor is far more than normal, and hence it's more likely to have electric discharge in transmission lines on such a way in such a day compared to the day with fairly clear weather. The system has to design taking those extreme situations into consideration. Conditions of cable for corona in transmission lines. This particular phenomena depends highly on the conductors and its physical conditions. It has an inverse proportionality relationship with the diameter of the conductors. That is, with the increase in diameter, the effect of corona in power system reduces considerably. Also, the presence of dirt and roughness of the conductor reduces the critical breakdown voltage, making the conductor more prone to corona losses. Hence, in most cities and industrial areas having high pollution, this factor is of reasonable importance to counter the ill effect it has on the system. Spacing between the conductors. As already mentioned, for corona to occur effectively, the spacing between the line should be much higher compared to its diameter. But if the length is increased beyond a certain limit, the dielectric stress on the air reduces, and consequently the effect of corona reduces as well. If the spacing is made too large, then corona for that region of transmission line might occur at all. Method of reducing corona effect. It has been seen that intense corona effect are observed at the working voltage of 33 kV or above. Therefore, careful design should be made to avoid corona on the substations or bus bars rated for 33 kV and higher voltages. Otherwise, highly ionized air may cause flashover in the insulators or between the phases, causing considerable damage to the equipments. The corona effect can be reduced by following two methods. First one, by increasing the conductor size. By increasing the conductor size, the voltage at which corona occurs is raised, and hence corona effect are considerably reduces. This is one of the reasons that ACSR conductors, which have a large cross-sectional area, are used in transmission lines. Second, by increasing conductor spacing. By increasing spacing between the conductor, the voltage at which corona is raised, and hence corona effect can be eliminated. However, spacing cannot be increased too much, otherwise the cost of supporting structure, that is bigger cross arms and supports, may increase to considerable extent.